So this session, so the first 20 minutes is kind of slides and just to introduce you all to the concepts that are going to be needed for some of the rest of the workshop. And then we'll start getting into more hands-on sort of sessions. And I'd like to first start by saying that we're going to be doing quite a lot of the interactive discussion on the Discord. So hopefully all of you were able to join, and you would see that there is already a bunch of channels in the training workshop. So in Event General, there are these links to the GitHub repository and so on. And in this first session, which I'm presenting now, there should be a poll, which would love to have your input already, or you can also provide it as we go through. So this is the question: how would you characterize the current state of the art in protein complex prediction? This can be protein-protein or protein-ligand. So what we wanted to do is kind of get to the level of breakthroughs in structure prediction. And one thing that's kind of important to know or understand is that breakthroughs require generalization. So what I have here is from CASP15. It's a plot of all of the monomer structure prediction results across the years. So each line is sort of the best method from that CASP, across the different targets. And so you'll see that here there's AlphaFold, and then here there's AlphaFold 2 in CASP14. And what's important to know is that we stratified these targets, right, based on how easy they were to predict. And here, easiness was just based on how many of similar structures had been seen before in the PDB, homologous structures. And the reason that AlphaFold 2 was a breakthrough in monomer prediction is not because it performed well in easy targets. Most of the methods were already doing that. It's because it performed well irrespective of the difficulty of the target. So it generalized across different kinds of targets. So when you look at the PDB, when you look at new, in this case, protein ligand complexes released in the PDB, they're often not novel, they're often not difficult. So here what we have is for every year, the PDB complexes, protein ligand complexes that were released, and the color sort of represents how novel they are. So what you need to know is the white bars are the ones where it's less than 30% sequence identity of the protein. And as you'll see, every year, even though there are so many complexes released, most of them are not novel. Most of them have very similar protein sequences, very similar ligands as what's been seen before. And so if you do a time split, what you would get is an overestimate of model performance. So if you do just a split on everything after 2022, what you get is mostly easy targets. And this is also the case in protein ligand datasets. If you do a time split, you end up with complexes that are very similar to what you are using in training. So you wouldn't really be able to tell if you have a breakthrough. Another really important thing, so until now, this was about AlphaFold 2, which was for monomer prediction. The definition of novelty kind of depends on the task that you're doing. So in our case, when we're talking about protein-protein interactions or protein-ligand complexes, the difficulty is defined by the similarity or the novelty of the interaction or of the interface. So here's an example from Pinder where from protein flow, where they split based on sequence similarity of the proteins, but you still end up with proteins in your training set and your test set which have identical interfaces. And with ligands as well, it starts getting more complicated. You can have cases like this where the protein is exactly the same, but the ligand is now in a different pocket, and it's a different ligand. So actually, can your model, having trained on this protein ligand complex, can it actually predict that this ligand actually goes somewhere else? And the same thing for different ligands in the same pocket. Maybe the pocket changes, but the ligand stays the same, or everything is different. And essentially for protein complex prediction methods to be useful in real life scenarios, they have to be able to generalize across all of these different situations. And so both Pinder and Plinder actually measure cluster and split based on these interaction similarities. So similarities which are relevant for the task. The other thing that's really important is quality. So experimental structures vary a lot in quality. So for example, here we have a protein ligand complex, right? And there's a lot of missing atoms in the, this should say residues. So there's missing atoms in the pocket. There's also cases where you can have alternate configurations of the ligand. So if you would say that this is your ground truth and your model predicts this, then you would be unfairly penalized because this is also true. And you have cases where interactions are kind of spurious just because it's a crystal contact, or it's not a biologically relevant interaction. Or you have cases where there's a huge gap between the interfaces. And again, this is not something that you would really want to reproduce when you're training your methods. And this is something that we actually found becomes really important for measuring performance. So we need reliable ground truth for evaluation. And what we found is that irrespective of whether you're measuring performance on an easy split or a hard split, if you use the complexes with high quality, high experimental quality, you will have a higher success than if you have lower experimental quality. And this is not the model's fault, it's just that the ground truth is not reliable. So this is really important that we have reliable ground truth for evaluation. So with these two things in mind, we can start splitting. And we used kind of the same way of splitting for both Pinder and Plinder, where essentially we wanted to split the entire PDB of protein-protein complexes or protein-ligand complexes such that we get a test set that is high quality, that is diverse, but most importantly, is different or difficult, has a range of difficulty compared to the training set. And so this was basically done by using this graph where each complex is connected based on their interaction similarity. And then if you choose something for the test set, then you basically remove all of their connected complexes from the training set. And in this way, you get a test set that satisfies your criteria of high quality and diversity, while still being able to evaluate whether your method actually generalizes across novel proteins, novel ligands, novel pockets, and so on. So what happened when we used this kind of method and measured method performance is that their performance completely dropped. So in this case, we have two protein-protein interaction methods and one protein-ligand interaction method. First evaluated on the deleaked set. So this is like basically the time split version where a lot of the complexes are easy, and then evaluated on the difficult set. So after doing this splitting to have more difficult complexes in the test set. And you see that the performance drops. So essentially these methods are memorizing what's in their training set and are not able to generalize. And if you plot that actually as a measure of this similarity to the training set or the distance from the training set, you actually see that the success rate follows this trend of being great when the complexes are similar and not so good as soon as you start getting far away. And this trend probably seems familiar to you from the CASP plot. Essentially, we are at a stage where we don't yet have a breakthrough for complex prediction. And so this was sort of, all of this was sort of our motivation to build Pinder and Plinder to try and address these issues. So, sorry, next, forgot one thing. This is very important. The other really important thing, so until now, until this point, it was just talking about complex prediction. But a lot of the times, complex prediction has been benchmarked as rigid redocking, meaning that you already have the bound structures of your two proteins or just your protein, and you put them together. Your model just predicts how they go together to predict the interface or to predict where the ligand goes in. And this is not realistic because you don't actually have the bound structure. What you can have is an apo structure, which may be in a different conformation, or which may even be blocking the active site, or you could have a predicted structure, where, for example, in this case, you can see that the prediction is very far from the truth. And in this case, actually, because this predicted structure has this very long tail, it has blocked the active site and prevented the method from predicting the interaction in the right place, which should have been here, and instead predicted it here. So rigid redocking is not realistic. And this is what we also find when actually evaluating methods is they may seem great. So this is Vina's physics-based method. This is for protein ligand complex prediction. And essentially higher is better for this metric. You'll learn about this metric in the next session. But they may seem great if you start with the bound structure, but as soon as you start with a predicted structure, the performance goes down. And the same for PPIs. So they may seem great when there's not a big conformational change, but as soon as that you start having a conformational change, then you're no longer able to do docking. So this means that we need to take flexibility into account when training our methods, when evaluating what is a good method for docking or for complex prediction. So we actually need to go beyond rigid placement RMSD and look at the pose, the pocket, the interactions. Are we getting all of it right? So that irrespective of what kind of conformation we start with, we are able to get to the complex. Okay, so Pinder and Plinder put these concepts all together to make it's an end-to-end reproducible dataset creation workflow. So this is for Pinder, goes through the entire PDB to get all of the interacting domain pairs, then also pairs them with APO and AlphaFold2 predicted structures, stratified by this flexibility, so the level of conformational change. Does this kind of splitting, as I mentioned before, based on having a high quality test set that is also difficult compared to the training set. Similarly, a high quality validation set that's difficult compared to the training set. And then with all of these, can evaluate the performance of methods, both from the axis of can they generalize, and from the axis of conformational flexibility, how difficult the starting structure is, can they go to the answer? And it's pretty much the same for Plinder, but then from protein ligand complexes. So again, collecting all of the protein ligand complexes from the PDB, pairing them with APO and predicted structures. In this case, we have quite a lot of different kinds of similarity metrics since there's two different objects. So at the protein level, pocket level, interaction, and ligand levels, using those to split, again, maximizing the test set quality and diversity while minimizing the leakage to the training set, and evaluation from these two axes of flexibility as well as similarity to the training set, so generalizability. And just to also give you a teaser on how this would help with training your models, basically having these better data sets and splits can lead to better models because you can train them better. So here we have examples from the Pinder paper where it was DiffDock PP, rigid PPI docking method, trained on DIPS dataset compared to trained on Pinder dataset. And you see that the performance increases quite a bit. And if you actually look at the performance as a function of similarity to the training set, as we were looking at before, you see that using the splits, this kind of split that we provide that basically has these difficult cases, allows you to better monitor your training to get a method that actually generalizes across all of the different similarity thresholds. So this is what we provide, right? So the training sets are much bigger, so they're much bigger and more diverse, so your model can see more kinds of complexes. The validation set, it has a lot of difference from the training set, so it's actually you're able to measure generalization on the validation set to stop the training at the right time, to make sure you're not overfitting, to make sure you're not underfitting. We provide these linked APO predicted structures that you can augment your training with, so that you can actually teach your model how to deal with conformational flexibility. The test sets are high quality and diverse, so they are reliable ground truth, and they are diverse enough to be able to show model performance on different kinds of complexes. And the inference is realistic because you start from the kind of structure that a user would start from, which is an APO structure or a predicted structure. And the evaluation incorporates this kind of flexibility as well. So that's what we are hoping to introduce you all to today, and hopefully incorporate into your methods and models. And basically, let's try to get to a place where together we can go to this next breakthrough in complex prediction. Okay, so that's it from my side from the concepts perspective. I just wanted to also quickly introduce how the notebooks are going to work. So we have a couple of hands-on sessions. These are available in the Discord chat and also from the GitHub. So basically in the README, if you click on Open in Colab, then you have the notebook in Colab. And there's 3 notebooks. So for all 3 of them, there's 2 steps that kind of have to be run to install the dependencies. And I just wanted to go through that already now, because it's better if you can run those 2 either in the break or during the presentation, so that you have the installations ready, and then you can just start from the content. And the presenters of these sessions will also be doing that. So they will be starting directly from the content. So it only takes like 3 to 4 minutes to install, though, just to give you an idea of the time. So what you would need to do is first run the first cell. And as this runs, it will restart the kernel. So wait until the kernel restarts. It will say your session crashed for an unknown reason. Wait until that happens. And then run the second cell. And then you have all the everything installed to run the entire notebook. And of course, if you have any issues with this, please get in touch on the Discord chat, and we're all on standby to help. Yeah, that's it from my side.